Hi, my name is Nicole Fry, and this is Lab 3 Black Hole. The purpose of this lab is to create a computer model that not only shows the trajectory of a star, which is the system, orbiting around a black hole, but to further analyze a star's motion with knowledge of the mass of the star, the position of the black hole, however, no known knowledge of the mass of the black hole. We want to analyze the motion of the star as it orbits the black hole in order to find the net force acting on the star, and to use this knowledge to estimate the mass of the black hole. So our overall objectives include analyzing the star's motion, calculating the net force on the star throughout its entire orbit or trajectory, and then determining the mass of the black hole. One of the bigger physical principles being used in this lab includes Newton's law of gravitational attraction, which states that every particle attracts every other particle in the universe with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. We will also use the momentum principle to relate the change in momentum on the net force, F-net. In lecture, we learned that the change in momentum is proportional to the net force times the change in time. Because of our knowledge in vectors, we know that the net force and the momentum will point in the same direction. The momentum principle is very helpful in this lab because we can break up the momentum into its parallel and perpendicular components, dp dt parallel and dp dt perpendicular. When we do this, we also obtain the parallel and perpendicular components to the net force. This is helpful because dp dt parallel tells us if the system's speed is either increasing or decreasing, and then dp dt perpendicular tells us if there is any change in direction in the system's momentum that will lead to a curvature that we would see later in the lab. When creating the computational model, I set the initial conditions such as defining the star's mass to be 2 times 10 to the 30th kilograms and the black hole's position vector to be the 0, 0, 0 meters. The while loop will iteratively calculate the displacement and velocity of the star, as well as advance the clock by delta t after each iteration. To calculate the net force, I calculated the list of initial and final velocities and found the initial and final momentum by multiplying the star's mass by the initial and final velocities respectively. Afterwards, I calculated dp dt by dividing the change in momentum by the change in time, and because of what we learned about earlier, dp dt is equal to F-net. As I already mentioned, we need to break the F-net into its parallel and perpendicular components to calculate F-net accurately and successfully. I did this first by calculating dp dt parallel, which involved calculating the direction of the momentum p hat and calculating the magnitude p dt, and multiply these values together to obtain dp dt parallel. Because we know that the sum of the parallel and perpendicular components is equal to dp dt, we can find the difference in dp dt and dp dt parallel to calculate dp dt perpendicular. After calculating the net force, we use this value and set it to the gravitational force acting on the star using the universal gravitational constant. Then we would rearrange the formula to solve for the black hole's mass. As you can see on the bottom images, to the left you have more so the arithmetic idea of what we'll be doing for the calculation, and then on the right is the coding aspect of the calculation. After running the code, we can see the star's orbit at 4 different times. In the animation, the orange vector represents F-net, the magenta vector represents F-net perpendicular, and then the light blue vector represents F-net parallel. Below you can also find the calculated magnitudes of each. One thing to note is that F-net is always pointed towards the black hole because of the gravitational force only acting between the two objects. And also, F-net perpendicular is always pointed inwards to the kissing circle, and both F-net and F-net perpendicular have larger magnitudes. The closest star is to the black hole, which follows the law of gravitation, which tells us that gravity is greater at shorter distances. Also, you can see that F-net parallel is always parallel or anti-parallel to the star's motion, which causes the star to either speed up or slow down. The average black hole mass that we calculated was 1.42 times 10 to the 34 kilograms, and you can also see the span of deviation. From this, I calculated the coefficient of variation, which was extremely small, which means that my calculations for the black hole's mass was actually pretty accurate. Now moving on to the discussion questions. First, what does it mean? In your analysis, you should discuss how the net force and its parallel and perpendicular components are different from the rate of change in momentum in its parallel and perpendicular components. So I said that the F-net and dp dt are not the same. Although they have the same direction, they are distinct from each other in how they are calculated, as well as what they tell us about the system. F-net causes the momentum to change, so therefore we could say that F-net is more so the cause, while dp dt is more so the effect. Secondary, what if? Imagine the black hole whose mass you found was removed, and a different black hole was placed in the same location. Assume the motion of the observed star remains unchanged and it's affected only by the gravitational force of this new black hole. Would you be able to tell a difference? I said yes, you could tell a difference because the star's motion would change due to the new gravitational force exerted, which depends on the mass of the black hole. Therefore, you could also calculate the new mass of the black hole as well. This is all for the lab. Thank you for listening.